see. 9 to the 4x equals 27 to the x minus 1. Again, if the bases are the same, the exponents are the same, and you can equate them and solve them. Are the bases the same here?
No.
No, they're not. I've got 9 and 27. Yeah, I want to change them to a base of 3 each, because they're both multiples of 3, right? So what could I change 9 to make it a base of 3? 9 equals 3 to the power of what? 2.
So would you add the 2 and the 4 together?
You would multiply them. Okay, what about 27? Can I write that as a power of 3? Yeah, 3 to the power of 3. Good. Okay, so I'm going to make these two substitutions in the left side and right sides respectively. So the left side becomes 3 squared, which is what 9 was, all raised to the power of 4x. And then I have 3 cubed, which was what 27 was, all raised to the power of x minus 1. With me? And then following the exponent laws that I had last time, these two guys get multiplied, and these two guys get multiplied. Okay, so it's going to look like this. We're going to go 3 to the power of 8x, and that's just 2 times 4x. And then up here, I'm going to have 3 to the power of 3 times x minus 1. That whole thing gets multiplied by 3. Okay, so I have 3 to the power of 8x equals 3 to the power of 3x minus 3. Good? And again, what do I do here?
Solve x.
Yeah, solve for x. How do I do that? What do I write next? Yeah, make the exponents equal. And again, I can do that because the bases are the same. Okay, so I have 8x equals 3x minus 3. Solving for x just gives me 5x equals 3, negative 3. So x is equal to negative 3 over 5. Good? Pretty simple? Okay. Again, the key here is realizing that sometimes you'll need to change the bases on one, sometimes you need to change the bases on both. But the goal is to make them the same. And once you do that, the algebra is pretty simple from there. Okay, D is a little tougher. D is a little bit of a tougher problem. I've got 2 to the 2x equals a quarter to the power of x minus 1. How can I make these bases the same? I've got a base of 2 here and a base of 1 over 4. Is there any way to write 2 with an exponent to get 1 over 4? Give you a little bit of a hint. Notice that I have my base in the numerator of a fraction here and in a denominator over here. How do you take a base and relocate it to the denominator of a fraction? Negative exponents. Right? If I raised 2 to the power of 2, sorry, I should stay in blue here. If I raised 2 to the power of 2, that would give me 4, which is almost what I want. But I want 1 over 4, so I want to flip it, right? So if I raised it to the negative 2, then that would flip it to 1 over 4. Does that make sense? So I can rewrite 1 over 4 as 2 to the negative 2. Follow that line of thinking? Okay. So I'm going to have 2 to the 2x equals 2 to the negative 2. That's what 4, or 1 over 4 became. All to the power of x minus 1. Okay? Then I'm going to multiply in that negative 2. So I have 2 to the 2x equals 2 to the negative 2 times x minus 1. And then we'll just multiply that in. It's negative 2x plus 2. And now my bases are the same, my exponents are the same. You tell me the value of x. Okay, so 2x equals negative 2x plus 2. Bringing this guy over gives me 4x equals 2. dividing both sides by 4. After I reduce, I get a half. Okay? So you see how this method works, right? Make the bases the same, equate the exponents, you're good to go. What would you do, just thinking about this a little further, what would you do if I gave you something like 2 to the 3x equals 3 to the 4x? Is there any way to change these bases so that they're the same?
You have to go to 6. You'd have to go to 12. No.
It'd be difficult, right? This is where logarithms come in. Okay? So like I was saying earlier at the beginning of the lecture, the examples that you're using today are fabricated, are made specially for the method that you're using, where you make the bases the same and then the exponents the same. Okay? But logarithms are a more general method. See? Useful, right?